are going to talk about a new type of function. So last quarter we talked about linear and we talked about quadratic. This quarter we're going to talk about exponential. Okay, so on your paper, I want you to underline exponential. Okay, what it means to be exponential is to have an x in the exponent. This is what makes it exponential. Okay, so on the table, we're going to fill in some x and y values. Okay, and then we're going to actually graph it. Okay, so on here, you good? All right, keep passing on those actually. Yeah. Oh. Okay, so we're going to graph this and we're going to fill in the table. Okay, so we're going to just take some x and y values. So give me some x values. Maybe we want to try plugging in 0, maybe 1, maybe 2. Okay, so if we plug 0 into this equation, 2 to the 0 power is what? Not 0. Anything raised to the 0 power is 1. Okay? What is 2 to the first power? 2. And then 2 to the second power? 4. Okay, so we're going to graph these points. We've got 0, 1, 1, 2, and 2, 4. Let's just say if we plugged in 3, what will we get? 2 to the third power. That's going to give me 2 times 2 times 2. What's 2 times 2 times 2? Not 6. 2 times 2 is, and 4 times 2 is 8. Does that make sense? Good. Now, when we connect these dots, we're going to have something that looks like this. Okay. Give you a second to finish drawing that. So again, we're going to have this little like shape. Okay, so where did it cross the y-axis? Where did it cross the y-axis? Yes. You can have anything that's in that box over there. It crossed at 0, 1. Okay. Did it ever cross the x-axis? No. So there are no x-intercepts or none x-intercepts. Okay. This gets really, really, really close, but never touches. Y'all know what that is called in the math world? Okay, so this is going to be called an asymptote. Exactly, an asymptote. So don't touch the asymptote. The asymptote is where it approaches but never touches. Okay? So there's an asymptote at y equals 0. Okay, so right here, this horizontal line is y equals 0. That's the asymptote. The like line in blue. Okay? Now, for our domain for all of our exponential functions, that's going to be negative infinity to positive infinity. Domain for all of our exponential functions is going to be negative infinity to positive infinity. Okay. Our range is going to be a little different depending on the function. Our range is going to be our lowest to our highest. Well, we have an asymptote at 0. So it goes all the way down to 0, but never touches. And then it goes to positive infinity. So we go from 0 to positive infinity. Notice how I used parentheses instead of brackets on this one. And for transformations, we're just going to say that it has a base of 2. We're not going to say anything else. Just going to leave it like that. Okay. So on this one, what's going to happen is we're going to plug in these numbers. Okay. So this first one is going to give us 1. If we plug in 1 in here, we're going to get 1/3. If we plug in 2, we're going to get 1/9. Now, you probably got some decimals, right? You probably got like 0.3 repeating. And then when you typed in 1/3 raised to the second power, what'd you get? It's the dead silent for me. All right, you plugged in 1/3 and you raised it to the second power. What'd you get? So what's the y-intercept of this one? That's going to be 0, 1. Okay. Let's focus. Come on. Okay. If we actually graph this, it would look something like this. It's almost like the opposite of what we just saw. Okay. Because this is going to be called decay. So the last one we had growth. This one is going to be called decay because the number that's inside is less than 1. So decay is the number that's inside is less than 1. Now there's no x-intercept. For the transformation, our base is just 1/3, but that doesn't really mean that anything has changed. Our our asymptote is the same. It's still going to be y equals 0. Our domain is going to be the same. But now what's our range on this one? What's our lowest y value? It goes all the way down to the the x-axis, and then goes above. So our range is going to be from 0 to positive infinity. All right, on the next one, we have this 3 raised to the x minus 2. We're going to take that and we're going to actually plug it in. Now, when you do this, you need to make sure that you use parentheses around the exponent, because otherwise you're going to get something else. So here's what our graph looks like. I'm going to go ahead and pull up the table. Okay. All right, so on here, you can go ahead and write this out on your table. So just do 0, 1, and 2. Thanks, babe. Then just grab that paper. Okay, so go ahead and write 0, 1, and 2 on the left-hand side. And then you're going to write 0.1111, 0.333, and then comma 1. And go ahead and plot those 3 points on your graph. Take a second, write those down. So again, you should have on your paper wrote 0, 0.111, 1, 0.333, and 2, 1. When you graph those, you should have gotten something like this. Is this going to be growth or is this going to be decay? How do we know? It's growing, as well as this number right here is bigger than 1. This number right here is bigger than 1, so this is going to be growth. Okay? Now, where did it cross the y-axis? Crossed at 0, 0.111. And where did it cross the x-axis? Well, did it? No. Okay? There's no x-intercept. Now, is there an asymptote? Does it like get really close but never touch something? Yeah? Where is that at? Y equals 0. With asymptotes, you have to write it as an equation. With asymptotes, you have to write it as an equation. If you don't write it as an equation, it's wrong. Okay? What's our domain for exponential functions? What's our domain for exponential functions? Negative infinity to positive infinity. Don't get that one wrong, please. Okay, what's the range? 0 to positive infinity. Here's the new part. Transformation. When we looked at our graph, we've got this. Let's say that we got rid of that minus 2. Okay, I'm going to erase this really quick and I'll put it back in a second. Okay, let's say we got rid of that minus 2. So we would just have 3 raised to the x. What happened from the blue to the red? What happened from the blue to the red? It went to the right. It shifted right. How many units? 2. Everybody see where I got that from? Okay. Also, look at our equation. We have this x minus 2. So it's opposite of what we think. We're moving to the right 2. So for our transformation, we're going to say right 2. Great. But when you type this into your graphing calculator, you really have to be careful about how you type it. You want to type it like this. Okay. Notice how I put parentheses around the 3. Okay. I raise the x. That +1 is not in the exponent. Okay. If you type it in the exponent, it's going to change how you do, like how the graph is. Okay. So again, here's our table. We got 0, 1, 2. We got 0, 3, 1, 7, and 2, 19. Okay. So when I fill this in, 0, 3. 1, 7, and 2, 19. Okay, it's gonna look something like this. 6. Okay. Is this growth or is this decay? Growth, how do we know? Because it's growing, or we can look at this number and it's bigger than 1. You need to be able to do it with an equation or with a graph. What's our y-intercept? So 0, 3. Do we have an x-intercept? No. What's our domain for all exponential functions? Okay, what's our range? Does it go down to 0? Do we have a number that's in between 1 and 0 for our y values? No. If we look at our equation from this graph, where does it kind of get close to but never actually touch? So looking at this, it gets closer and closer to what? All right, guys. What is it getting closer and closer to? 1. Okay. So we have an asymptote at y equals 1. And our range is going to be from 1 to positive infinity. Okay. Fun fact, whatever number that's added out here is what your asymptote is. Okay. Transformation, we're going to have a vertical stretch of 2 because it's the number that's out front. And then we're going to have a shift up of 1 because that's +1 that's on the outside. Okay. And you can compare this to, let's say you took off the 2 and the 1. If you compared it to 3 raised to the x and you looked at this graph, if you compared green to black, do we see how it went up? And it also is stretched. So it's pulled a little bit higher up. Okay. Go ahead and finish writing that down. So in this unit, they're going to ask you oftentimes to compare exponential to whatever other function. Okay, so that's probably going to be linear or quadratic. So right here, looking at this equation, what type of function is this guy? Is there an x in the exponent? Oh. No. Is there a squared over the x? No. So this one is going to be linear. Okay. And the way we can verify it is by taking all these x values and plugging them in. So I'm going to help you with this one. So if I plug in -3, I'm going to get -6. If I plug in -2, that's going to be -4. If I plug in -1, I'm going to get -2. If I plug in 0, I'm going to get 0, then 2, then 4, then 6. Okay. Now, do you remember back in the last unit where we said, if we find the first difference and it's all the same, then it's linear? Well, watch what's going to happen. If I find the first difference between these numbers, I take -4 minus -6, that's going to be a difference of 2. And that number is going to be repeated all the way down. So the first difference is 2. So the methods we can use to verify it is if the first difference is the same, Or we can look at the equation and see that we have this in this y equals mx plus b form. Okay, if I plug in these numbers, I would get 9, 4, 1, 0, 1, 4, 9. Okay, if I found the first difference, this is going to be 4 minus 9, which is -5. 1 minus 4, which is -3. 0 minus 1, which is -1. 1 minus 0 is 1. 4 minus 1 is 3. And 9 minus 4 is 5. If I found the second difference, because we see that this is not linear, because it's not the same for the first difference. If we try to find the second difference, we're going to see that the second difference is a difference of 2. And so since the second difference is the same, it's going to be a quadratic. We could also look at the fact that this has a squared in the exponent. So it's x squared, or the second difference is the same. So if we plug in these numbers, what'd you get for this first one? What'd you get for this first one? Okay, so when you plug this in, okay, you should get 1/8, then 1/4, then 1/2, then 1, 2, 4, 8. When we subtract, we're going to get something like this. Okay. And then if we subtract again for the second difference, we're going to get something like this. Are the first difference the same number? No. Is the second difference the same number? No. But could we take these numbers and multiply them by something to get the next number? Yes. And that's going to be 2. And this is called an exponential function. What was the number that we used to get the rest of the y values? That's going to be 2. Because look at what the base is on this guy. Since it has a ratio, this function is going to be called an exponential. Okay. You're also going to see with exponentials that the first difference and the second difference are going to be the same. There's a pattern that's going on. It's just a little different each time. Okay. This should be a 0.25. I apologize. So what I want you to do is on number 2, I want you to identify what type of function this is, either linear, exponential, or quadratic. Okay. You need to try this because this is going to be on your EOC. This is going to be on your final exam. Okay. Go ahead and take a moment. Try this on your own. I don't know. We're going to find out. All right. So let's take a look. So on this first one, okay, what'd y'all come up with? Is it linear, exponential, or quadratic? And how do you know? Okay, why do you say it's exponential? Yes, Alejandro. Why is it quadratic? Because the second difference is the same. Good. So this guy is a quadratic. Okay, what about the next one? So are we adding the same number each time? I don't think so. What if we found first difference? And then if we found the second difference, is that the same? No. Okay, so what is that one called? An exponential. Okay. What about the next one? If we found the first difference? On this one, it's a little bit harder to see because there's x values are going up by 2s instead of 1. Okay. But as long as it's consistent, then you should be able to see it. Another way you could have done this is you could have gone into your Desmos and you could actually type this straight into your table. Okay, so again, if you went into Desmos, let's say that you didn't know about the first and second difference. And let's say that you wanted to go in here and you wanted to create a table. You can hit this little plus sign and you can add a table in here. Okay. Mm-hmm. Okay. Now, when we look at the, yeah, that's the number right there. When we look at this, what shape is this making? Is this a straight line? No. Is it kind of like a curve that makes a U shape? No. So what is this one going to be? An exponential, right? Okay, so the third one is an exponential. Okay, what about the next one? Are we going up by something consistent each time? Yes, we're going up by 0.2 each time, right? So that's going to be linear. Exponential, quadratic, or linear. Reminder that a linear function looks like y equals mx plus b. A quadratic has an x squared, and then a exponential has some number raised to the x. See if you can figure out which one's which. So, really quick, if I continue to see blank papers, I'm going to quit printing out stuff for you. I'm going to make you handwrite everything. Okay? So, please, please, please make sure that we're writing stuff down. On this first one, okay, this has an x in the exponent, so that's going to make this one exponential. Okay? Did you hear me or y'all are still talking? So an x in the exponent makes it exponential. Okay? On the next one, this is y equals mx plus b, so this is going to be linear. This is like this one. Okay? On the next one, we've got a squared in the exponent, so that's going to make it quadratic. So what would number 4 be? Yep. Linear. Okay. What about number 5? Exponential. Okay. What about the last one? Quadratic. Okay. Please let that be easy. Like, let it be easy. You just have to memorize these 3. Okay. All right. Go ahead and take a moment. Try to answer the next couple. Okay. On number 1, is it exponential, quadratic, or linear? Sebastian. Is it exponential, quadratic, or linear? Yeah. Why? Why is it exponential? Oh, okay, cool. Okay. On the next one, Aiden, what is it? Give him a second. Wait a minute. It's linear. Why is it linear? Y equals mx plus b. All right, number 3, Alejandro, what you got? Quadratic. John, what you got on number 4? Okay. All right, number 5, what we got? What is it? Linear? Okay. Number 6, what do you have? Quadratic. Let that be the easy stuff. There is always at least like 1 or 2 problems that's like, what type of function is this? Let that be easy. Okay. Yes, I would have said it. It'd be like that. Okay. This is the part where we start to compare. Ready? So this unit is talking about comparing the different types of functions. So for instance, in this next one, it says an insect, the length of I don't know how to say that word, correlates to the number of eggs in a clutch. For the following 2 data sets, which one shows more eggs at the length of 305 millimeters? So what are we looking at? We got 2 different functions. We got a table, we got a graph. Okay. Looking at when x is 305, what is roughly our y value for this guy? Hey, pay attention. This is important. Ready? We're about 7, right? If our length is 305, our y value is 7. Looking at our table, if we're at 305, what's our y value roughly? It's in between 11 and 12, right? Which one has more? The table. So table has more. So everybody see how that goes? Okay. Sometimes they'll ask you something simple like this. Sometimes it might be a little bit more advanced. Go ahead and flip over to the next page. Okay, this is where exponential functions are important. So fun fact, my little brother is a financial planner. And so basically what he does is he talks to millionaires and they come in and they're like, hey, I want to plan out for this situation, either their house or their kids or whatever. Okay. Say again, like a yacht? Yeah, that's a thing too. Sometimes they're buying insurance and that kind of stuff. Ready? Okay. So what he does is he takes an exponential function and he projects their lifespan and how much money they should invest and at what rate and that kind of thing. Okay, so exponential functions can make you about $120,000 a year, depending on what job you have. Okay, so if you know how to work this stuff, it's really important. So your financial advisor presents you with 4 exponentially growing plans for retirement. All dollar amounts are given in millions. Okay, so for example, 0.025 million is really $25,000. Explore your options and answer the following questions about those retirement plans. Okay, so you have these 4 different plans, okay, and we're trying to answer these questions, okay? So I would suggest first, maybe either writing out these as an equation or trying to figure out what's going on each time. So first of all, plan A, it says the company will put in an initial amount of 0.025, okay? And is going to get a return rate of 5%. So the way we write this equation is we're going to say A is our initial and B is going to be our growth rate. Okay? So when we write out this equation, we're going to say 0.025, because that's what we started with, times 1.05. We're going to raise it to the x. The reason why we put 1.05 is because we can't just have 0.05 here because we won't have the amount that we've already gotten plus some. Okay. Plan B already has their equation. On plan C, what are we multiplying by each time? Well, can we figure that out? Yeah. Our growth rate is going from 0.022 divided by 0.02. If we divided that, that's going to tell us what our growth rate is. So 0.022 divided by 0.02, that's going to be 1.1. Our initial was 0.02, and we're multiplying it by 1.1, and we're raising it to the x. I know I hit you with a lot of information, so let's talk through this again. This is basically your equation for exponential functions, your initial is always going to be that first term out front. Your growth rate is going to be this b. So the first question that they ask us is, what is the lowest initial investment? So looking at our different equations, the initial investment that's out front, which one has the lowest? Which one has the smallest number that's out front? B, okay? And that amount is 0.01, right? What's the next lowest one? C. Okay, what's the next lowest one? A. And then what's the highest one? D. Okay. Next one is asking for the highest growth rate to the lowest growth rate. So we're looking at the percentage for each one. Okay. So for instance, over here, if we took off this 1, we would have a 5% return rate, right? If we took off this 1 over here, this would be a 15%. If we took off this one right here, this would be a 10%. What? So in order to figure out the growth rate on this one, we're going to take 0.06 and divide it by 0.05. The reason why we're doing this is we're taking the second term divided by the first term. So if we take 0.06 and we divide it by 0.05, that's going to give us 1.2. Well, 1.2, if we take off the 1, that means we're going to have a 20% growth rate. Which one has the highest? Plan D. Okay. And then what's the next highest? Plan B. And then what's the next one? C and then A, right? If we come down here, we're going to say plan D, B, C, and A. And that was 20, 15, 10, and 5%. Okay, so each scenario has been graphed and shown below. Okay, so it's done it for you. And we want to see how long it's going to take in order for us to make $1 million, right? Everybody wants to make $1 million at some point, right? No. Oh. Okay, but if you had $1 million, you could own a Porsche. So, wow. Okay, so what we want to do is we want to look at when y equals 1 million. Well, remember, our stuff is written in millions of dollars. So we're going to look at when y is 1, what is our x value? So for this first one, how many years? So if our y value is 1, what is our x value? 75. So it would take 75 years in order for them to make $1 million. On the next one, if we look at when y is 1, about how long is it going to take for it to hit $1 million? We can say a rough estimate. Let's say 34 years, roughly. Okay. Yep. 34 years from now. Okay. What about the next one? Well, when y is 1, what was our x? Like 40, like 1 or 2, right? And then what was how many years after would it take for plan D? It's like 16-ish. So which one would you prefer? Would you want to have $1 million in 16 years, 42, 34, or 75? 16 years. So plan D is probably going to be the fastest, right? It gets you to $1 million a lot faster.